Good afternoon, everyone. So, in the last video, we went through a simple example comprised with data set related to height and weight, and we saw that the moment we step from univariate analysis to multivariate analysis, we could make some conclusion, we can draw some new insights, and then we also talked limitation as a human when it comes to analysis of more than two-dimensional data set, or let's say three-dimensional data set. Beyond that we can't visualize. And then we kind of highlighted the importance of um, data dimension technique, for example, principal component analysis that reduces the dimension of the data and kind of simplify it for visualization, that it provides some sort of key factors, and we can kind of play with those important components and kind of make new conclusions. So in this video, what I'm going to speak, like how do we really do this dimension reduction in chemometrics. To demonstrate that, I again take a very simple data set, and the idea behind this video is mainly to show you that how the um, rotation of the axis or the projection of a data in a new space can lead to simplification of data, or in other words, like dimension reduction, and it kind of simplify the data, retaining all the variation within our data set. So for that, I take a very simple uh, two variable data set, which basically x1 and x2. And if you really look, um, you have kind of a significant variation of this set of data along x1 axis. So you see they have variability right from here and it goes up to here. And it also has kind of high variability along x2 direction. So this data has sort of kind of having a lot of variability along both the axes. So now, how the dimension reduction technique will be helping us. So what usually they do, they just rotate one of, uh, not one, in an orthogonal fashion, they give rotation to each one of these axes by, let's say, some degree. So in this case, I make a rotation of x1 in this direction, and then we have to ensure the orthogonality, so I give the same amount of rotation to the dimension x2. So in a picture wise you could see something like this. So now our new axis are along this black dashed line, and you know, so you have to ensure the orthogonality, so you give, as I mentioned, also the rotation to this x2 axis. So you kind of a new uh, space. So what you would really see that in the new space, if I kind of ignore the blue line and just focus on the black ones, you would see in the new space you have variability just along this new axis, right? The T1 axis. It doesn't have any variability along the T2, or in other words, along the x2 axis in our original space. So now this axis, right, the T2 axis has no meaning. So now if you really pay attention to this, in our original data set we need both axes to kind of explain the variability of our data matrix. But if you kind of give a rotation to your axis system, then you come to a situation where you don't need this vertical axis anymore. So all the variation can be explained just by studying the T1 axis, right? So it kind of simplifies the data set, reduces the dimension. Now you can take the same or the similar example at higher dimensions. So the algorithms, for example, principal component analysis, they do the similar thing for data comprising of 5, 10, 15, 20, you name it. They do similar rotation of the original axis and kind of uh, reduces the dependency on some of the original axis, right? So this is what we kind of went through right now. And in the next video, I will be talking about how to we do this projection, how do we derive this projection matrix, and what is this T, X, and P. So X is your original data for sure, but what is this T and P? What is their significance, and what are they? And you know, all those details we will be covering in the next lecture. So stay tuned. We look forward. Yeah. Bye bye. Have a nice day.